Good morning, everyone. My name is Mariah Smith. I'm sorry I forgot to wear my name tag this morning. It is my honor to introduce Professor Alden Griffith. Although Professor Griffith gave me permission to completely make up everything about him in this introduction, I will stick with the truth. I'm sure you will all be impressed to hear it. Professor Griffith is an assistant professor in the Environmental Studies program and the Biological Sciences Department, and the postdoctoral botany fellow in the Wellesley College Botanic Gardens. He received his BA in biology from Wesleyan University, not Wellesley, and his PhD in environmental studies from the University of California, Santa Cruz. Professor Griffith's research interests in plant ecology include invasive species, plant-plant facilitation, and the effects of climate change. He has numerous published works that were authored or co-authored in peer-reviewed journals such as Ecology, Ecologia, and Biogeochemistry, including his most recent on the effects of climate and snow depth on Bromus tectorum population dynamics at high elevation. He has received numerous awards and grants, including the David Gaines Memorial Award and Botany Fellow Research Funding through the Wellesley College Botanic Gardens. In recognition of Professor Griffith's deeply rooted passion for plants, I'm not only wearing a green sweater, but I'm encouraging all of you to visit the H.H. Honeywell Arboretum of the Wellesley College Botanic Gardens, which is adjacent to the very room we are currently sitting in. It is truly a hidden treasure on our campus and a location of sanctuary to, I'm sure, Professor Griffith and even myself. Professor Griffith's love of plants is also illustrated by his favorite words, fungible and caryophyllaceae, and his children's names, Violet and Field. But Professor Griffith's passions do not only extend to his love of plants, but also to his love of teaching. At Wellesley, he teaches the fundamentals of environmental science, plant invasions, field botany, environmental limits and conservation, and environmental horticulture. Professor Griffith contends that his deepest goals lie in the hopes that, quote, that all Wellesley students will graduate with an understanding of how their actions and decisions are connected to the world around them, and that they'll have a framework to critically address them. I chose to introduce Professor Griffith because I knew there must be an amazing reason why his name is not at all unfamiliar to me, although I have never had the privilege of taking one of his classes. His name echoes throughout our campus not because he shares our love for coffee, but because of the impression he has made upon students such as my best friend Carly Gale, who professed that, quote, although he may be quick to attribute his enthusiastic energy to coffee, which he mentioned as his favorite candy, students love the excitement with which he teaches each lesson. Alden is not only a great scientist, but also a great science writer. His ability to easily communicate even very complex topics, as well as his infectious passion that fills the room as he lectures, makes his classes a joy to attend. Even fleeting conversations with him are suffused with his genuine excitement about his work, about environmental science, and most especially about Wellesley. From what I have learned about Professor Griffith is that he hopes to utilize his understanding of, for example, climate change, to impress upon not only his students, but also to reverse the detrimental effects of climate change misinformation on the public. I think Professor Joyce would agree that Professor Griffith attempts to make well-informed information about the world's most urgent environmental issues a public good. And for that reason, Professor Griffith created a website called foolmeonce.com, devoted to offering, quote, something that is often missing from the coverage of climate change, thorough and accessible explanations of the most common and contentious claims. So do not be fooled twice, and never hesitate to frolic in fields of violets, for plants and our environment as a whole have great implications on our increasingly global world. Whether you are from India, or Lebanon, or the United States, or Zimbabwe, Singapore, or Hungary, Professor Griffith's lecture today will have the utmost relevance in all of our lives. Please join me in giving Professor Alden Griffith a big green welcome.
I don't think I've ever had such a wonderful introduction. So we're going to spend the next hour or so talking about climate science and climate change. Part of this is going to be really diving into climate science, but I also want to make sure that you guys recognize the sort of broader framing of what I want to convey here, which is sort of thinking about science, looking at science, dealing with science, and grappling with really complex issues. So I sort of want to start by trying to frame this in terms of why everybody is here, and not just at the Albright Institute, but why did you go to college? Why are you at Wellesley? What are you doing here? And there might be a lot of answers that, oh, I'm going to get a good education so I can get a good job, I can succeed. And that is something that as you're going through college, this is probably what you're thinking about, and that's what I was thinking about, et cetera, sometimes. But it's useful to flip it around and think about what are, from my point of view, from professor's point of view, why are you guys here? Why you guys are, throughout the course, are obviously carrying more than just a grade, but you are concerned about your grades. I'm not concerned about your grades. Right? What are we concerned about? Why are we thinking, what's so important about coming to college? What are we trying to do for you? What are you trying to get out of this? So why are you here? Yeah?
To become a more informed citizen and have a better understanding of the world that I live in.
Right, so what is that going to allow you to do? And how do you, every day, day to day, when you're leading your life, what are you doing that causes you to go on your certain trajectory, sometimes big, sometimes small? Yeah. Right, yeah. More that I've thought about this, life is all about just decision making. Whether it's professional, personal, huge decisions, small decisions. Ultimately, you're getting an education to try and learn how to make decisions, how to be informed in a way that you can critically engage in decision making. Right? So that's sort of the framework that I want to put out there in this, in terms of thinking about science, confronted with issues that are very complex, and nobody in this room is a climate scientist. I'm not a climate scientist. I've spent a lot of time learning about this. But how can we engage so that we can make the best decisions, right? Whether they're really important and have fundamental impacts on the world, or whether it's sort of daily decision, right? So that's sort of where I want to start. And then I want to zoom way back. I might want to turn off the lights. Is that going to put people to sleep? So has anyone seen this picture before? Yeah? What is it? What do you?
Isn't it Earth from 7 Rings?
Yeah, so this is probably one of the most amazing pictures ever taken. This little dot here is you, me, and everyone we know. That's Earth. It's from beyond Saturn's rings. It's from, it's from like 4 billion miles away or something. It's the furthest distance we've ever observed the Earth. And these are just light rays coming through. So it's just an amazing picture to look at and realize that everything we know, everyone we know, everything that's ever happened on Earth is sort of just sitting out in the middle of cold, empty space, right? And, oops, and why is it so cozy? Why is this all happening? Right? And so just to give a fundamental background before we dive into some things, all of our energy is pretty much coming from the sun. Basically, all of our energy is coming from the sun. And the sun's energy is coming in, this seems to be advancing doubly, I'll use the keyboard, is coming in and heating up the Earth. Right? And anytime, why is it going? Sorry. Anytime an object has a temperature, it's going to be radiating energy. So you and I are all radiating energy because we have a temperature. Right? So the Earth is warmed up by the sun, and as it warms up, it radiates energy back out, just like anything in the universe. Right? And this is visible light coming in. This is primarily infrared radiation going out. And at some point, there's going to be, assuming this isn't changing all that much, which in the long run, it hasn't been changing drastically, certainly not in a relatively short time periods. And the energy in and the energy out are going to balance out eventually. And you're going to get to some sort of equilibrium. And we can ask the question, well, what should the temperature of the Earth be if there is no atmosphere, if it was just a big ball of rock or water? And simple physics says it should be about minus 18 degrees Celsius, so it should be 0 degrees Fahrenheit, average around the world. Right? We should be more or less a frozen planet. And we know this isn't true. And this is because we have an atmosphere. This is because we have greenhouse gases in our atmosphere naturally occurring. Right? And greenhouse gases are extremely important because they take this infrared radiation that would be leaving the Earth, and they absorb it, or some of it, and then radiate some of that back down to the Earth. So it's really kind of, in many ways, it's like a blanket or a greenhouse. It's not exactly analogous, but it traps in some of this heat. Right? And it has a huge impact. The actual average temperature of the Earth is 14 degrees Celsius or 57 degrees Fahrenheit. This is a huge effect. And we couldn't possibly live the way we do without naturally occurring greenhouse gases. So they're very real, and they are very powerful. And everything we know, all of the ecological and agricultural systems that support us depend on this. All of the ecological systems that support diversity and wildlife depend on this too. So these are this is a very important aspect of the planet. So, and I should also mention that please feel free to ask questions along the way. There's a lot of content I want to get through, and hopefully we'll have some time to ask questions at the end. But if you're unclear about something, please jump in. So greenhouse gases are up in the atmosphere, and so far we're really talking about natural greenhouse gases. And by far the most important greenhouse gas is water vapor. It's on average is about sort of 4% of the atmosphere at any given time. And it's a powerful greenhouse gas. Right? And other greenhouse gases, such as carbon dioxide, which we'll be talking a lot about today, methane, or nitrous oxide, these are also important greenhouse gases, with of these carbon dioxide being the most important because there's relatively more of it. Right? But why aren't we concerned about water vapor? We're concerned about carbon dioxide as a greenhouse gas related to climate change. We hear all about this. Sometimes the argument is made, oh, water vapor is the most important greenhouse gas. That carbon dioxide is not a very important player. Well, a big key difference here is these are so-called long-lived greenhouse gases. When you put them up in the atmosphere, they can stay up there for a while and have an effect. Water vapor is very different, and actually it depends on the amount of water vapor in the atmosphere depends on temperature. So let's say we tried to warm the planet up by, let's say we wanted to warm the planet, right? What would we do? Let's say we pumped a ton of water vapor up into the atmosphere, as much as possible. What would happen? What would be the end result? It would rain. It would just come right back down. The atmosphere can only hold a certain amount of water vapor, right? So this is hugely important, but it's a natural factor, and it adjusts relative to the temperature. These you can actually control climate with. You can add carbon dioxide, and a lot of it's going to stay up there. Right? So that's a fundamental difference that's really important. So we're going to focus a bit on carbon dioxide because this is primarily of concern as we're burning fossil fuels. A byproduct of that is the release of carbon dioxide into the atmosphere. But it's not just the release of carbon dioxide, it's really the source that's important. You and I are releasing carbon dioxide right now as we breathe. Here's a factory, an old salt factory, and if you can sort of see down here the fuel, what does it look like they're burning there? Yeah, so they're burning wood here to help dry out seawater, I assume, and get the salt. And burning wood, though, you're basically just taking carbon dioxide that trees had taken it out of the atmosphere, constructed their wood out of that carbon, and then you're burning it and you're putting it back into the atmosphere. So you may have heard the term carbon neutral. This type of release of carbon dioxide, you're just sort of putting it, you're taking a scoop out of the bathtub that these trees absorb carbon dioxide through photosynthesis. They took that scoop out, and then you're just putting it back into the atmosphere when you burn trees. So that's very different. And if you burn through a lot of trees, like England did, and you may soon run out of trees, and then luckily discover large deposits of coal. So the Industrial Revolution was really, part of it was kicked off with this huge discovery of vast amounts of energy, right? And so here we're burning coal. This is a very different type of carbon. This is carbon that was stored underground for millions of years. It has not been in the atmosphere for a long, long time. It's out of the system, right? And as we burn it and continue to burn it in ever-increasing quantities, we're putting it into the atmosphere. And we're basically, instead of taking a scoop out of the bathtub and putting it back in, we're turning the tap onto the bathtub. We're adding a new source of carbon dioxide. And because it's a long-lived gas, it tends to stay in there. A large chunk of the carbon dioxide that we've put in the atmosphere is still there. But it is very complicated. There's all sorts of natural processes that carbon moves around the world. It goes in and out of plants and soil and back into the atmosphere. So where it is at any given time is very complicated, but most of what we've put in the atmosphere is still there. But ignoring some of the details of the way carbon dioxide moves around the atmosphere can get you into some trouble here too. So this is John Race. I think that's how you pronounce his name. He was a candidate for the US Senate in West Virginia. He did not win his race, but he has a statement that says the oceans that surround the world produce 185 billion tons of carbon dioxide per annum. Man per annum only produces 6 billion tons, so what could possibly be the concern? And aside from the fact that this number is wrong, which really doesn't matter, but what could possibly be the concern? He's saying that like the oceans release more carbon dioxide than we do. What's the big deal? What might you want to be thinking about here? What else might the oceans do? They take in carbon dioxide too. Right? They take in actually more than they release. Right? So this is a statement that is relying on one tiny aspect of the way carbon moves around the world and is really ignoring a key piece of the puzzle there. Right? And this didn't carry a lot of weight anywhere, but I found this really interesting, that you can make a statement that sounds really good. What could be the big deal? Well, you're ignoring a huge part of the science, right? So this is a big deal. And what's been going on here as we've burned fossil fuels? What I'm going to show is the last 400,000 years of atmospheric carbon dioxide concentrations. And carbon dioxide exists as a very trace gas in the atmosphere. There's not very much of it. There's, this is in parts per million. So for every million molecules, there's about there's about 390 or so parts, 390 carbon dioxide molecules for every million molecules. So it doesn't exist in a huge abundance, but it has a big effect. So this is the carbon dioxide concentration for the last 400,000 years, and I stopped it right before the Industrial Revolution, basically 250 years ago. And we know this from drilling down into ice cores in Antarctica, and then the different colors refer to different data from different parts of the world. But wherever you go, carbon dioxide is more or less the same. It's really well distributed. And you drill down into the ice, and you can find tiny little air bubbles that were trapped in there 400,000 years ago that it's a little time capsule of the atmosphere. So we have a really good record of what concentrations of greenhouse gases were. And if we start about 250 years ago and move forward, this is where we are right now. So well above anything that's happened in the last 400,000 years. These cycles here correspond to ice ages. This is ice age in this period. Carbon dioxide tracks very well with ice ages, and we're not going to talk too much about that. And that's actually a lot more complicated than some people make it seem. But we haven't likely been this high in terms of carbon dioxide, a major greenhouse gas, in the last 10 million years. So we're already really in uncharted waters. And a big question is, okay, well, what's going to happen? Where are we going to go? What are our emissions going to be as we burn more fossil fuels? And last year we had we burned the greatest amount of released the greatest amount of carbon dioxide into the atmosphere on record. Well, if we double carbon dioxide from what it was before the Industrial Revolution, about 280 or so down here. Oh, actually, I'm sorry. We're going to zoom in first to make this a little more clear. This is the last 20,000 years coming out of the last ice age. Right? And carbon dioxide has been pretty much very stable throughout the entire Holocene, through the period in which humans have, civilization has developed. And here we are. And if we keep on burning at the rates that we're burning, doubling carbon dioxide is likely to happen maybe mid-century or so. Right? At the rate we're going, we're very on track to do this. This is very, very likely. And by the end of the century, if we keep relying on fossil fuels heavily the way we are growing currently, we'll be off the charts here. We'll be up above potentially 800 parts per million. Right? So this is pretty astonishing, what we're doing here, this grand experiment that we're doing by just dumping all this greenhouse gas into the atmosphere and basically seeing what happens, right? Really in new territory here. But we can ask the question, the big question, what happens if we double carbon dioxide? And this is actually more complicated than you might think, because the simple, or the sort of superficial answer is actually relatively simple. It's sort of a calculation, that you can do. And if you double carbon dioxide, we know how much it absorbs radiation and sends it back down to Earth, and that would give a warming of about 1.2 degrees Celsius by itself. But the big problem here is that it's very complicated how the Earth responds to sort of, when you knock the climate, how temperature responds is very tricky. This is part of, highlighting the temperature change is very complex. And this is part of the Economist article that I had attached with my lecture here, sort of talking about different areas of uncertainty and what's causing temperature to change. And this is often known as feedbacks. And I just want to give some examples here. So what happens if we increase temperature? What's going to be a result of increasing temperature that might then feed back on temperature itself? Yeah. Yeah, so that's one example, that if you, actually that's the next one. If you increase temperatures, right, then you're melting sea ice. Sea ice is white, right? Or just ice in general is white. It's reflecting light back out into space. Now instead of reflecting, we're absorbing more of that energy, and it warms up even more, right? And so you get into this loop. And a similar one is when you increase temperatures, you increase water vapor because the atmosphere can hold more water, and you get warmer temperatures because water vapor is a greenhouse gas. Right? And then this other example, as you increase temperatures, you melt more ice. When you melt more ice, you reflect less and you absorb more, and you increase temperature even more. So these are ways that you can amplify an initial temperature change, right, by having this positive feedback. And there are a lot of these. These are some of the more prominent ones. But a big issue actually has to do with clouds, and we're starting to gain some clarity on this. But what happens when you increase water vapor? Do you get more clouds? Do you get fewer clouds? Likely, I mean, you think maybe you get more clouds, but there's a lot of other factors that go into cloud formation. But the problem with clouds is that high clouds tend to actually warm, low clouds tend to cool. So it's really, there are these feedbacks that are really tricky in trying to figure out exactly what's going to happen when you double carbon dioxide or when you change some factor of the climate. Right? So this is sort of a large area of the uncertainty in sort of the big picture temperature change. And this boils down to this question of how sensitive is the Earth's temperature to increased greenhouse gases. Right? Sensitive being a key word, and this is known as climate sensitivity. So you may hear this term if you start looking through climate change or global warming science papers or reports. This is basically saying, if we double carbon dioxide, what's the temperature change going to be in the end when all of these things have happened, all of these feedbacks have happened? And there are a lot of ways to look at this by going into the past. So looking at how temperature has changed during the last ice age, looking at how temperature changes during volcanic eruptions, by trying to model it. Basically, any time temperature has changed, you can ask the question, why did it change? And how much of a sort of nudge was that to begin with, and what was the eventual response? This is sort of these different ways to try and figure that out. And what's most important to point out here, so these are sort of different ranges, different probability ranges of what climate sensitivity might be in terms of degrees Celsius for a doubling of carbon dioxide. An important thing to point out here is that these are independent ways of looking at this, which is really key. Right? We're not looking at one thing to say, what's the temperature change going to be? We're looking at lots of different things that are entirely independent of each other, and they're all largely converging on a similar answer, right? Which is this sort of range here between 2 and 4.5 degrees of warming. So the kind of current consensus is if we double carbon dioxide, we're likely to see 2 to 4.5 degrees of warming around the world, right? Or 3.6 to 8.1 degrees Fahrenheit degrees Fahrenheit. Just to give you some reference points, that 3.6 degrees Fahrenheit is the difference between Boston and Lexington, Kentucky. 8.1 is Boston and Raleigh, North Carolina. Right? So this is a scenario that's potentially possible by mid-century, that we might get to this doubling of carbon dioxide. And these are really profound changes. North Carolina and Boston are really different, right? And another thing to point out is that there's a really high upper bound. If you sort of look at this, these tend to be kind of skewed this way, meaning that it's really hard to rule out some of these higher temperature responses. It's, there might be a low probability, but it's hard to rule them out as being impossible. Okay, so this was just a real big background on sort of how greenhouse gases affect the climate, why we're concerned about them, why this is really a sort of profound change that we've impacted in terms of the composition of the atmosphere. So I want to get into some questions that are really important here and talk about them in the context of how the public perceives these and how this type of information filters through from the science to the public in general. And these are the two big questions we're going to talk about today. Is the Earth warming, and are we responsible? And this is, if you hear the words scientific consensus on climate change, or the consensus on climate change, this is sort of largely the two questions we're talking about here. Is it happening, and are we doing it? Right? Those are sort of the big questions. Because if we're doing it, then that has huge policy implications in terms of what we need to do to fix it, right? So we'll start with, is the Earth warming? Okay, so we'll start here with, what does the public think? And this is polls conducted by the Pew Center over a number of years, and they asked the question, is there solid evidence the Earth is warming? And it's actually been declining over the last few years. It's come up a little bit in the last few years, right? Where 63% of the public thinks that, yes, there's solid evidence. Almost a full third thinks that there is not solid evidence. Yes?
I'm assuming this is U.S.
Yes, I'm sorry. This is United States only.
Is there any data from the rest of the world? Is this a trend? Or?
I think largely European countries, there tends to be more public support. I don't know exactly what the numbers are, but sometimes what's more interesting, rather than just what the overall numbers are, is how they change. And there are certain periods even in Europe too, where there's specific events that cause public perception to go down. Right? But this is United States only. Another question, or? Okay. So almost a full third of Americans say that there's not solid evidence. Right? And this is down from where it was half a decade ago. And what's really amazing here, this is a question that has to do with measurement and observation. Right? This is not about how do we respond to climate change, not what do we do, not what are the policy choices. This is just, is it happening? Have we observed this, right? And if you stop somebody on the street and you wanted to find out whether they were likely to believe in that the Earth is warming or not, probably the best way to ask or to find out is ask which political party they are part of. Right? So this is a huge shift, which is rather amazing. That sort of shows how some would say politicized, some would say politics have been scienticized, or whatever the word would be, but how this is such a strong overlap of science and politics that your conclusion as to something that is an observation and a measurement is based on what your political party is. So let's compare this to the public data to what scientists think. So 63% of the public thinks Earth is warming. Before we get to what scientists think, let's ask the question, well, what do people think scientists think? Right? So this is a poll conducted in 2010. This is the public's view of the scientific consensus. And they're basically split, that between scientists agree or there's much disagreement. Basically suggesting the public thinks there's a big debate going on, right? And if we look at one poll, and there's been other polls like this is a poll of over 3,000 Earth scientists, and there's been other polls and other surveys of literature, et cetera, and it always comes out like this, at least when it's, sometimes you have a poll of 5,000 geologists and 4,000 out of them happen to be oil geologists or coal geologists or things like that. So this is trying to be more of an unbiased poll here. And it's an overwhelming majority. And among active climatologists, it's almost everybody, 96%, says yes, the Earth is warming. Yeah?
Just a really pedantic point, but again, with the scientists, is that throughout the world or is that in the US?
I think this was from a U.S. meeting of scientists, but I believe that, I don't think it means it's exclusively U.S. scientists. I think it was conducted at a meeting, but it likely drew international scientists too. But I should say that for the purposes of this talk, this is largely framed in the United States. Mm-hmm. Okay, so let's look at this. Is the Earth, oh wait, no, before this, I want to, so what do people not only think of climate, what do they think of scientists? And this is an interesting poll that I came across, which is a Harris poll from 2008. And this is people being asked to more or less rate whether they think professions have very great prestige. Right? Are they respected? So we can start down below. Real estate agents got 5%, accountants 11, stockbrokers 13, lawyers 26, members of Congress 28, although that's probably gone down. Military officers, now we're getting into some prestigious jobs here, 51%. Teachers, 51%. Say this very prestigious. Nurse and doctors were saving lives, right? These are prestigious. Scientists, 57%, second only to firefighters. Like you have to go into burning buildings, saving children to be more, have higher prestige than a scientist. So it puts science in kind of a weird place these days, that it's highly respected. Public thinks scientists are very prestigious, but scientific conclusions are not getting through to the public. Right? Are we being ignored? What's going on? So this is a weird moment for science, particularly climate science scientists. Okay, and part of this may have to do with how people get their information. We're going to spend a little bit thinking, before we get to the question of is the world warming, we're going to start thinking about how are people getting information? What are some of these reasons where there's this big disconnect? Right? And obviously most people probably, they are not reading scientific papers. They're probably getting information, at least in part, through news outlets. Right? And you can find lots of headlines like global warming theory and chaos after report finds increased solar activity may cool the Earth, or more questions about the validity of global warming theory, et cetera. Right? So there's abounds with sensationalist headlines. But beyond just that, there may be sort of a more sort of deep-cutting aspect of journalism that may introduce a kind of bias in the way people get information. So if you're a journalist and you're trying to write a story, you want to appear to be objective, right? How do you do that? If you're talking about an area where there seems to be some sort of disagreement, you call up a climate scientist, and then what do? Who else do you call? Yeah. Yeah, so there's this journalistic norm of balance, right? That you want to present, you want to appear. I mean, I think that's actually Fox News's sort of tagline is fair and balanced, right? That we are presenting both sides of, which is in this case particularly ironic, but we're presenting both sides of the story. Well, when you present both sides of the story, when in the scientific community there's only really one side of the story, that actually can potentially induce a bias. So this is research, it's a bit dated at this point, looking from 2004, looking at the so-called prestige press. So this included several prominent newspapers in the US, like the New York Times, I think the Wall Street Journal, maybe the Washington Post. And they were scanned through these different articles on climate change and said, are they presenting a sort of conclusion that's in line with the majority of scientists, or are they presenting balanced account? And more than half of them are presenting a balanced account. Right? So here's this side, here's this side. And similarly, with television, we see this even greater fraction that more than 2/3 of television news articles were saying here's climate scientist A and here's climate skeptic who disagrees with climate scientist A. Right? And if you start paying attention to a lot of this, you realize that most of the climate skeptics who are invited on tend to be the same people over and over. But so this is one potential way that there, and this has been changing a bit. There are some news outlets that really seem to be writing a bit more in terms of what the science is actually saying. But this is one way in which we may have sort of had this delayed response among the public. It doesn't necessarily explain the recent decrease. So another way is, publications that are out there. These are books that you can buy that present a very nicely packaged, very compelling case of why, this is how Mother Nature fools the world's top scientists, the global warming deception, how a secret elite plans to bankrupt America and steal your freedom. So this might not have as much to do with climate science, but it's probably, I have not read this, I admit, it is probably portraying a lot of information trying to convince you that the science underlying it is incorrect. Right? And one aspect of this is it's kind of easy to do this. And I could have come in here and spent an hour convincing you all that climate science is a giant hoax. And I probably could have done a pretty good job at that. And you'd walk out being very confused and thinking that you've been lied to, right, by climate scientists. There's also this idea of what's out there now. There's so much information out there. People don't necessarily get an unbiased source of news anymore. People are often searching out their news. Right? You get a lot of information from blogs or from a particular news outlet. This is also kind of known as echo chambers, that you get your news from this area and you stay in there and that's it, right? And you don't really hear all of the information. This is a search I did last year on Google. You can search for blogs and search for homepages of blogs. And I typed in global warming and got these responses here. The first one that comes up, globalwarming.org, if you go to that, looks like it's got all sorts of information here. There's Global Warming 101, get beyond the hype, get the facts. If you scroll down, this is a product of Competitive Enterprise Institute, which is a organization whose their stated goal is to promote free markets and limited government, right? And which, there's nothing wrong necessarily with that. But this is very different from promoting free markets and limited government. This is providing lots of information about climate science that kind of supports that view. And you may have a lot of middle schoolers or high schoolers searching for global warming, going, oh, top Google hit, and they go to this site. And they get a lot of information that is really not aligned with what climate scientists largely say. And if you count, I counted the top 40 of these and then got kind of sick of going to all of these different sites. And I tried to assess whether they were sort of convinced of climate scientists or skeptical of it. And it's about evenly split. Right? So it's sort of 50-50. If you are looking at blogs out there, you're going to get this big storm of information that makes little sense if you're trying to put it all together. So this is just one example, too. This is a site called Watsup with That, which, this is winner of the 2008 Weblog Awards for the best science blog. This site gets like 100 visitors a year. I would urge you not to, or I would urge you to take everything on this with a grain of salt. This is just one post I want to highlight. This is a post, there's tons of posts all the time. And basically what he's trying to say, these are two different temperature analyses of the world. This is NASA's, this is University of Alabama. And the post is that for, I think, November 2010, that this one is 0.74 degrees, the temperature anomaly, 0.74 versus 0.38, so a lot higher. And the conclusion here is that NASA must be cooking the books, because why is NASA's temperature so much higher than the satellite temperature from Alabama over here? And what he doesn't point out to you is that these are temperature anomalies, meaning that they're reference to some base period. They're a deviation from some average. And that's really the only way to compare temperature stations in Greenland versus Brazil. You can't just take their average. You have to compare them to some sort of base period. And they have different base periods. This temperature analysis spans over 100 years. Its base period is from the middle of the 20th century. This base period this temperature one only goes back to 1979. Its base period spans the latter part of the 20th century. So they're really like apples and oranges. You can't compare them because their zero is different. They're completely different. Right? And this was pointed out to the author here, Anthony Watts, and instead of correcting it, he just goes on this big rant in the comments thread about people. But I mean, this site gets a lot of visitors. And imagine sort of a top finance blog making a big deal out of a difference in price and forgetting that one's in euros and one's in dollars, right? It really, in this case, it's really that simple. And there are a lot of fancy analyses on here with lots of graphs and lots of data, which I'm not going to show you for different ones. And for one post with all this fancy-looking graphs, in the comment thread, Sean D says, "I agree, this is real science, but I have no idea what it means." Exactly, right? It looks really good, but it's really hard to critically examine. Right? And these are the things that I really want you guys to be thinking about, like whether or not you have the immediate capacity to examine this, which almost nobody does. And this is what drove me into being really interested in this, is I would hear these presentations and think, that can't be true, because it really conflicts with what I've been reading, but I just don't know. I don't have the ability to stand up there and debunk that right now, because climate science is just huge. It's this enormous, complex thing. And how can anyone just debunk a claim, right? There's also very documented organized opposition, and I don't want to say that there certainly are environmental groups, right? And I want to be critical of what they're advocating and how much they're basing things in reality. But I think it's fair to say that those with vested interest in climate change not being an issue are a little bit on a sort of different level here. This is a memo from 1998 from the American Petroleum Institute with acknowledged and credited contributions from Exxon and Chevron and the George Marshall Institute. The George Marshall Institute, by the way, was very instrumental in trying to downplay the effects of secondhand cigarette smoke and promote uncertainty and say that we don't know enough about this, that smoking doesn't cause cancer, et cetera. They are downplaying the effects of ozone, and now the same exact people are downplaying the effects of climate change. And in this memo, this is the Global Climate Science Communications Action Plan, and they say victory will be achieved when average citizens understand or recognize uncertainties in climate science. Recognition of uncertainties becomes part of the conventional wisdom. Let's play up uncertainties. Right? This is a big, complex area. There's tons of things to play up. That the media understands and recognizes uncertainties in climate science. Media coverage reflects balance on climate science and recognition of the validity of viewpoints that challenge the current conventional wisdom. And so this is part of a strategy laid out. Industry senior leadership understands uncertainties in climate science, making them stronger ambassadors to those who shape climate policy. Those promoting the Kyoto Treaty, so the international agreement to limit greenhouse gases, on the basis of extent science appear to be out of touch with reality. And then unless climate change becomes a non-issue, meaning the Kyoto proposal is defeated and there are no further initiatives to thwart the threat of climate change, there may be no moment when we can declare victory for our efforts. Right? So there's clearly a strategy behind the scenes here, and in many cases it seems like it's been working. Right? Then there's also people like me. That's actually scarier than when it's that large. It's kind of scary. But scientists are a different lot and tend to play by different rules. Scientific norms are very different from political norms. In politics, if you say something that might be borderline untrue, et cetera, people kind of tend to forget about it a week later. And if you're following campaigns, there's claims going left and right about various things. Right? And in the realm of science, scientists are very reluctant to say anything that they don't feel very, very strongly about. Because your career is really based on your objective interpretation of data, and not going out on a limb and on something that's kind of shaky. Right? No one wants to be sort of attacked for supporting a theory that really wasn't robust. Right? So scientists are inherently conservative in that we really want to make sure things are strongly supported before we go out and advocate them. So scientists tend to be hesitant to be advocates, right? They're scared of being labeled an activist, scared of losing your objectivity, right? So scientists, and climate scientists in general, have started to change and address this, realizing that there is a role for scientists to be advocates, certainly at least for their data and their conclusions, right? But But so scientists really need to start playing a better role here too in trying to communicate. And we're seeing this. And another thing I want to point out about scientists is that, I kind of wish that we hadn't let this word skeptic kind of become what it is. So a climate skeptic is someone who is skeptical of that climate change is happening, right? And all scientists are skeptics. We're inherently skeptics. We're hard to convince. We see somebody else's paper and we want to figure out what's wrong with it, right? We're trying to make sure that our peers are at a level, and we're holding them up to a high level. We're very critical and very skeptical, right? So I think by nature, scientists are very skeptical, right? And should apply that skepticism equally over everything, not just on particular one side of an issue. And then this is really large, I think, in terms of how the public perceives science. And the Economist article talked about this. And this gets to potentially how it's so easy to distort climate scientists. And that the public may see science as a house of cards, right? And what happens when you knock one card out, right, and the whole thing falls apart. And this works really, if this is how the public perceives science, then there's an easy strategy to trying to confuse the public when it comes to scientific matters. Just throw a lot of things at them and make it look like you're knocking out a lot of cards, right? And so it sort of emphasizes quantity over quality, sound bites over explanation. And over a period of a few years, people say, wow, I've read so many headlines about this one paper that came out and refuted climate change. Like, these cards are being pulled, the whole thing must be collapsing. But if this was the case, science wouldn't be anywhere. We wouldn't be nowhere. All of our great scientific advances can't be built on as a house of cards. And so scientists tend to have a different viewpoint, and I really like this analogy of viewing science as a jigsaw puzzle. Right? We're putting in pieces. You don't have to have all the pieces in place to see the big conclusion. Right? Climate science is never going to be proven or completely without uncertainty. No science ever is. Right? And some pieces might not fit, and we may have to take them out. Right? But that doesn't make the whole thing fall apart. So all of the things that science have given us and technologies that have come out of science, this model is really a stronger foundation for that. Right? It's always being challenged and is really robust. And all these pieces represent these sort of independent pieces, right? That you can't prove or disprove climate change based on one thing. You never will. Okay? So I think this is a really important thing to be thinking about when you're critically engaging something that you are sort of confused about or aren't really sure because your expertise isn't in that area. Start to think about, okay, well, how does this fit relative to everything? Is this the silver bullet? Is there such thing as a silver bullet or smoking gun? Right? So I want to present you with this. This is mean global surface temperatures from the 3 major data sets here. And we have no warming for over a decade. It's 13 years, most of your life. We see pretty much a flat trend here. Right? So this is overall global surface temperature anomalies. So, what do you do when you're faced with something like this? This is often presented, right, as being strong evidence against climate change, as evidence here with global warming has stopped. There is a problem with global warming. It stopped in 1998. There's been no global warming since 1995. Global warming stopped in 1998. Right? So this claim has really gone around. What do you guys do when you see this? What do you want to know? If the claim is that climate change has stopped. Yeah.
What did it look like before?
Yeah, right. So how do you put this in context, right? This is from starting at 1998 through now. What is this relative to the rest of the temperature trend? What else might you be interested in? Yeah. Yeah, in this case, I'm not sure that would make as much of a difference because the base year tells you where 0 is on the scale, but doesn't change the scale. So it wouldn't do anything to change whether this is sort of, like 0 here is kind of irrelevant to the actual question of temperature change. It just happens to be the spot that they use as a reference. But in some cases, when you're comparing things, you really want to know, are they on the right scale for sure? Yeah. Yeah, you might want to know why. What's, temperature change, it doesn't just exist as data points. What's going on? And we'll get to that later. Yeah.
I guess I want to know some other measures of warming, like the ocean temperature or maybe sea ice melt.
Great, yeah. Is this a silver bullet? No, there's a lot of ways in which we look at temperature change. Yeah, maybe one more. Yeah.
I was really curious as to what the typical variation is in a year. Temperature, like over a 10-year period, 100 years ago, what was the graph?
Yeah, exactly. What's the greater context? So the first comment was, what was it before? So, and then also, so what's the variability through time? And then also, what's the sort of short-term variability, right? So these are all really important. These are just waveforms. So this is, let's say this is some sort of cycle like El Nino, which in El Nino years it tends to be warmer. It's just an exchange of heat around the planet, right, from the oceans to the atmosphere. Let's say this is sort of a solar cycle, and this is some other factor, right? So we have some cycles, and then we have an increasing temperature trend, right? And when we add them all together, we know it has to go up because we put it in there. We have 100% information here. And when we combine all of these, we get a really complicated signal, right? Short-term trends go up and down, up and down, up and down, up and down. Long-term trend is up. It has to be up because we know it's up because we made it to go up, right? And so this is all about sort of looking at overall variability and putting it in context. So let's do that here with this data set, put it in context before 1998. I'm going back now to 1979, and I'm only starting there. That's where a lot of other measurements begin at 1979. I'll show you more data earlier, but that's just often a place to start and doesn't really make a difference where I start. But you can see it seems to fit right in there, and 1998 was particularly really warm. So if you start in that year, that's a pretty good place to start if you want to get a flat trend, right? And it doesn't seem to be all that different from what we've seen before. We can also ask, well, if global warming is continuing, what should we expect? So let's cut out this period and look at the earlier period of temperature rise, which has a significant slope. And let's say, OK, if this is true and this is continuing, where would we expect temperatures to be? We'd expect them to be somewhere around here, right? And we put this back on. There they are, right? In fact, they're slightly above it. Right? So this isn't sort of the end-all analysis here, but there's no way from this to conclude that global warming has stopped. There's no evidence there. It's really just in line with kind of what we would expect, right? And this requires really examining the full picture. And if we examine the even fuller picture, looking all the way back to the 19th century, this is the global surface temperature that we see, right? A really strong rise, particularly starting around 1970 or so. But this has been criticized because, well, how reliable are these thermometers, right? When you have long-term data sets, you're always concerned that measurements are really comparable. Do we really know that they're really good, et cetera? And then there are some pictures here of an official temperature station next to an air conditioner. Pretty bad place to put a temperature station, as this is always going to be giving off hot air. This one people love to show. It's above a barbecue, right? So how can we rely on temperatures stations if these are some examples? And this is an analysis that Anthony Watts, the guy who actually runs that watsup with that website, he started a project with lots of volunteers to go around to all these stations and categorize them or classify them based on whether they meet certain criteria as being good or poor, et cetera, and found that most of them, so this is blue and green are the good stations, orange and red are the poor stations, the vast majority of a little more than 1,000 stations seem to be don't meet standards. Right? And this is a legitimate concern. We should be really concerned about the quality of our temperature data. But there's a whole other thing entirely to then start to draw conclusions from this. Right? So he's written several reports here. This big, long report. Is the US surface temperature record reliable? How do we know global warming is a problem if we can't trust the US temperature record? The conclusion is unescapable. US temperature record is unreliable. It follows that global database is likely similarly compromised and unreliable. Right? Well, what do you want to do, though, if you want to actually answer this question? What would you guys want to do? What type of analysis would you want to do? Yeah.
Do you look at data from other countries?
Right, and we will Well, this type of data, I'm not sure if it really exists as much in terms of the classification, at least I'm not sure of. But we will look at a larger picture. Yeah. Right, like do the analysis separately, and let's compare the good and the bad, right? Right, so there's behind the scenes on this, there's a lot of complexity because some of these temperature stations are, things have been changing around these temperature stations, including the temperature stations themselves. The thermometers that are there now are not the same ones that were there in 1940. We've upgraded things. The air conditioner that's there and the highway that's next to it wasn't there long ago. So there are these things behind the scenes that require adjustments, and temperature data are always adjusted to try and deal with this, right? To try and get rid of these. When you have a temperature record that goes like this and then shifts up 4 degrees, something was wrong. That was a measurement error or something. So there are all sorts of adjustments, right? But if you do this sort of standard adjustment that is done everywhere to look at temperature analyses, and I should mention across the globe, if you do the adjusted versus the unadjusted temperatures, you get the exact same answer. But if you look at the best or worst stations, this is analysis that Anthony Watts himself did finally, after several others had done it. Our picture of the temperature record in the US is exactly the same, whether you choose red, the worst, or white, the best. Right? So in the end, it makes no difference. There are differences in terms of maximum and minimum temperatures, et cetera, and which aren't necessarily trivial, but the overall picture in terms of how it informs climate change and global warming, it makes no difference, basically. And what, though, if we look at the total surface temperature across the land? So this is land surface temperature, not oceans, for the main 3 data sets. And people have criticized these data sets. This is a group in England, NASA, and then National Oceanic and Atmospheric Association of the US, of sort of, they've been doing this for so long, they're kind of stuck inside their shells that they can't really be trusted anymore. So a lot of climate skeptics were very excited when a new analysis came out this year, conducted at Berkeley by a more or less climate skeptic himself, and this is what they found, right? The exact same thing, right? But these are independent analyses of the same data, temperature stations around the world. What about completely independent analyses, which some of you mentioned, right? Let's not look at surface stations. What if we look at satellite temperatures, which don't measure temperature? They measure like microwave radiation upwelling from oxygen atoms based on their temperature. Like very, very different way of looking at temperature. This is surface temperature from 1979 on with a decadal warming of about 0.15 degrees Celsius per decade. That's the trend line. If we look at satellite temperatures, totally separate, right? We see a statistically indistinguishable trend. Right? They're slightly different. There are reasons why they're slightly different. But if we only had satellite temperatures, our conclusion about the last 30 years of temperatures would be really the same. Right? And we have a lot more than that. We have surface temperatures. We have satellite temperatures. We have radiosondes or weather balloons. We have ocean heat content, right? And if we look at the period where they all share data, overlap starting from 1979, they all tell us the same exact thing, right? And the probability of all of these being wrong is pretty low. But when we're talking about global warming, we usually are talking about temperature of the atmosphere, surface temperature. That's what we're used to. That's what matters to a lot of things that we can relate to. But global warming really is ocean warming. The vast majority of the energy that's gone into, that the Earth has absorbed, the extra energy, has gone into the ocean. So this is not looking at temperature, but looking at total energy content. So this is measured in 10 to the 21 joules, a huge amount of energy. This is how much energy has gone into heating the land and atmosphere. This is how much energy has gone into heating the oceans. Right? And just to put this into perspective, in 2008, the entire world energy consumption from burning fossil fuels, from burning everything, driving cars, moving ships, heating our homes was 500 exajoules around the world. In 1 year, the same time period, the ocean increased 10 times as much in terms of its energy, which is kind of amazing to think if we wanted to increase the energy content of the ocean and we put all of our energy use to doing that. We converted every house boiler and car and tanker, truck and ship to make heaters that would go into the ocean. Right? This is how much warming we get. But the byproduct of all of our energy use from putting fossil fuels into the, or from putting carbon dioxide into the atmosphere is having a far greater impact. Right? It's really astounding. And you probably have heard of in the rainforest, X amount of football fields are lost every second or so. I forget exactly what the one is. But over this time period, since every day since you guys have been alive, the oceans, the energy content in the oceans have been increasing by about 2 Hiroshima bombs per second. Right? So it's like every day of your entire life. It's an insane amount of energy that the Earth is absorbing and changing. And just to sort of hammer it home, these are all these different metrics that we look at to see is the Earth warming, and it is really unequivocal. Right? That every way we look at it, we see that it is responding in the way we would expect with a warming world. Right? And then if we look far back, the last 1,300 years, these are different ways, again, different independent ways of trying to reconstruct temperatures from the past using tree rings, using corals, using sediments. And they basically all tell the same story, that where we are right now, land temperature is higher than it's ever been in the last 1,000 years or so. And yet there are some amazing statements that go around, and not just go around on the internet, but in this case get presented to Congress. Lord Christopher Monckton has presented to the House of Representatives, I think, 3 times, been invited to speak. He is not a scientist, but he's speaking on matters of climate science. And he made this argument using this chart that the globe is actually cooling. Says the right response to the non-problem of global warming is to have the courage to do nothing. There has been global cooling for 7 years. So he shows this chart of satellite temperatures declining over 7 years. Right? And having just seen all these examples of temperature, we know that 7 years seems like a really short period of time to be looking at a temperature trend. Right? And if we really look at this is what he's talking about. And if you put all the data in, basically we've had temperature declining, declining, and declining again, even though it's always increasing, which makes no sense. Right? So this type of analysis is really easy to do, to refute and show that it's really trivial and doesn't add much to our understanding of climate change. But this is what's being presented to our members of Congress. And he also says that Arctic sea ice is, quote, just fine. And he shows 2 pictures here. Ignore the white part on the continents. I think in 1980 we didn't have the ability to measure snow cover then. So this is January 1980, January 2009. The pink area represents sea ice cover. Right? And if you squint your eyes, maybe you can tell a difference or maybe not. And he's showing 2 data points. Right? So I'm going to show all of the data of Arctic sea ice melting starting in 1979, so in the last 30 years or so, coming down. It's coming down really dramatically, and this colorful chart is going to get even more crazy in 1 second. We expect Arctic ice to melt and be at different extents for different times of the year. Say in summertime versus wintertime, things are going to be different. So I'm going to put trend lines on there for each time of the year. And in the winter months and spring months, we have the lowest decline in sea ice. In the summer months, the late summer, September, we have the greatest decline in sea ice as concurrent with warming. And those 2 points that Christopher Monckton showed are here and here. So he shows less than 1% of all of the data to make his claim. One which happens to be below the trend line in the beginning and above at the end. But let's do a similar thing. Let's just pick one trend line and look at the summer melt, the time of year when we've seen the greatest decline. And this isn't just interesting to look at because it's the greatest decline. This is really important for organisms that live up there. For polar bears, summer sea ice is habitat. Right? That is how there's a whole community of organisms that live underneath the ice. Polar bears hunt on the ice. This is important habitat. And it's declined about 2.5 million square kilometers in the past 30 years, which is sort of hard to put into perspective. But it's the entire east of the U.S., or east coast of the U.S., east of the Mississippi here. Right? So we've lost this much ice in this September in the last 30 years. This is one of the most profound changes we've ever observed on the planet. And if you look at all the data and really critically engage it, Arctic sea ice is really not fine. Right? So are we responsible here? This is the second part of the question. And again, I want to look at what the public thinks. And this is, again, from the Pew polls. Warming is due to, this is of the people who agree that the planet is warming. So it doesn't add up to 100%. Warming is due to human activity, natural processes, or don't know. This, again, has also been declining in recent years, right? With almost half the, about half the amount of people thinking that it's natural versus it's human activity. We can do the same analysis looking at what the public thinks versus what scientists think. So again, this is what do people think scientists think. Again, it's evenly split. So the public seems to think that there's a big debate out there in terms of whether it's caused by humans or not. And if we look among scientists, among active climatologists, there's 97% of them think it's caused by humans, right? So this figure shows that more graphically in terms of the 3 out of the 97 who are sort of saying, no, it's not caused by us. And this analogy is often used, but I think it's pretty powerful that if you thought you were sick and you went to a doctor, or sorry, went to 100 doctors and asked what was wrong with you, and 97 of them said you have a serious condition, which may be very problematic in the future, but we can fix it if we act now. And 3 of them said, don't worry about it, you're fine. You'd probably be interested in going with what the 97% said, right? So this is analogous to what's going on in climate science these days. And one thing that I think is really interesting is when so-called climate skeptics look at a graph like this and see that it's not warming, right, which presumably supports their point of view or their assumption of what's going on in the world, there are very few questions asked about what's causing this to change, right? When they see a warming trend, then there's all sorts of explanations to try and figure out why it can't be true, right? It's got to be some other solar activity or something, or it's got to be temperature station error. Right? So really applying different sort of reasoning filters on different parts of the curve. When this is supporting a certain viewpoint, doesn't matter what's causing it. It's great. But I want to get into what is causing this. I want to be skeptical of all of the data and try and figure out what's causing climate to change and think about what do groceries have to do with climate. And how many of you are econ majors? Okay, so there's a good chunk of you in there. And there's a lot of the same sort of reasoning and critical thinking applied to whole different areas of data analysis and thinking about trends and thinking about the world. And this is US retail grocery sales from spring 2008 into February 2009. Right? And having looked at the previous graph of climate and analyzed it, we would be reluctant to conclude immediately that, oh my goodness, retail sales are going down. Right? And part of this is because we want to look at the overall trend, right? But we also want to know what's causing it. Right? And when you look at this, right, we see lots of cyclical patterns. We see this is always low, right? This is always high. What's going on here? And so you guys have probably heard of seasonally adjusted data, right? We're trying to compare things, trying to account for external factors that are influencing this, and we want to really see what the real trend is. And this is actually fairly easy to do in a limited sense. The Census Bureau has their own way of doing it. But if you just look at the number of days in the month, February is always the lowest here. Well, it's got 28 days versus 31 days. So if you account for that, for these differences, you start to reduce this variability. Right? And if you say, well, what about the number of days where there's lots of feasting, or months where there's lots of feasting, like December and November, that people are buying tons of food, right? And so we're starting to reduce the amount of variability. The Census Bureau has their own way of seasonally adjusting it. And you see a much finer track here. And actually resolve some interesting patterns. Like right here, December 1999, big grocery sales. What do you think was going on? Y2K. That's what I'm assuming, right? People are freaked out. So we want to be able to not just understand what's the variability in context, but what's causing it. And so in this case, if we look at the raw data, which could be presented to you saying, oh, it's a downward trend, you would think, well, that's silly because we've got to see it in context. But even beyond just the context of the raw data, if you account for all these other factors that are going on that are sort of masking potentially masking the real trend, when you adjust it, you see it's not very special over this period. It was pretty much normal when you account for all these other factors. So we can apply the same sort of critical analysis to this warming signal and really ask, okay, what's causing it? And there are lots of different ways to do this. This is not the end-all way, but it's one way to start to say, okay, let's take these very natural factors that might be affecting climate and see what their influence is using this statistical technique. So some of the things that might be affecting climate over short-term periods, sort of the three main things that we could think of is El Nino. Okay, so this is a huge exchange of heat between the atmosphere and the ocean. And so in El Nino years, like this is anyone from California? Do you guys remember 1998? Super wet year, big El Nino year, right? So that strongly affects temperatures around the planet. We also have the influence of the sun. No climate scientist is ever discounting the influence of the sun. Certainly the sun can and has been influential on climate. Is it influential now? If we look at the total energy coming out of the sun, it goes up and down every decade or so, but there's no trend, right? It's not going up or anything. And if we look at volcanic aerosols, when you have huge eruptions that put a lot of reflective particles high up into the stratosphere, they can cool the planet. So this is Mount Pinatubo in 1998 that led to a short-term cooling of the planet. These are the things at this time scale that might be important. Natural factors. Let's try and figure out what happens when we start to include these and account for them. So here's our unadjusted data, just going back to 1979, this time frame that we looked at before. Let's account for El Nino. Right? And so now what we're doing is we're trying to statistically at least take the influence of El Nino out of the picture. Right? And there's good reason for including El Nino. We're not just putting in random things. And so 1998, when you account for El Nino, the temperature is now lower. It was higher than it would have been in the absence of El Nino. Same in 1983. And then in recent years, we've had a few strong La Ninas, meaning that it tends to cool the planet. So temperature was cooler than it would have been in the absence of this La Nina event, right? So we have this adjusted curve. Well, let's include now the effect of the sun and see if we pull out the effect of the sun, what are we left with? Right? And the main thing that stands out here is we've had actually a really long period of sort of quiet solar activity in the last decade or so. It's been relatively low. I don't know if any of you have been taking astronomy classes, but it's something that you may have come across. And so temperatures have been slightly lower, not dramatically, but slightly lower than they would have been had the sun been constant, right? And if we look at the effect of aerosols from volcanoes, Mount Pinatubo basically disappears. Right? If we didn't have the eruption of Mount Pinatubo, we wouldn't expect that decrease. And so now we're taking natural factors, and we're actually, by accounting for them, we're actually making the linear trend more strong. Right? So if natural factors were very important here at driving this temperature trend, when we account for them, we'd expect the temperature trend maybe to come down or not be all that strong. And instead, we're getting rid of the wiggles, and we're sort of making more clear this really strong trend. And so if you look at the last 13 years and actually ask the question, why might it be flat, and try and account for that, and granted, this is just one way, this isn't taking into account everything, but it elucidates that we probably would have continued to see a temperature rise had all these factors not been operating, right? All these natural factors. And so, this doesn't stop some people from making conclusions, like Ron Johnson, who's now a senator in Wisconsin, says, I absolutely do not believe that the science of man-caused climate change is proven, not by any stretch of the imagination. I think it's far more likely that it's just sunspot activity or something just in the geologic eons of time where we have changes in the climate, right? Well, it's really easy to look and try and see what's been going on with the sun, which we just did, what's been going on with sunspots. Sunspots, this is over the last 100 years, very similar to the total energy output of the sun. Went up a little bit beginning of the century, but then it's been leveled off, hasn't really done much. And as we've seen many times now, especially in the last 35 years or so, we have this huge rise, right? There's very little evidence that sunspots have anything to do with this, right? And just to list a few more so-called human fingerprints, really emphasizing the need for independent observations. There is no such thing as a silver bullet, right? We have measured less heat escaping out into space, less infrared energy, and we measured it at the wavelengths where we would expect greenhouse gases to be absorbing it. Right? We've seen that the Earth is out of energy balance, meaning that it's warming up to try and get back in balance. We've measured increased greenhouse gas radiation, basically the signature of that warming coming back down. We've measured that. We see nights warming faster than days on average, right? Meaning that greenhouse gas radiation is warming the planet all the time. Solar activity is warming the planet really during the day, right? So, and this isn't going to be the critical factor here, but it's just one of many. We see a signature here where lower atmosphere is warming, the upper atmosphere is cooling. The physics behind this is really tricky, and even I don't totally fully understand it, but this is a signal we'd expect for greenhouse warming, right? And not something like solar warming. We see air and oceans gaining heat. It's not just an exchange of energy around the world. Everywhere we look, we see energy going up, right? And really, there's no plausible natural mechanism for the last 35 years of warming. Earlier in the century, we do see some effect of these natural factors, but nothing's really happened in the last 35 years. Well, temperature has gone really up really quickly, and temperature does not change for no reason. And then along with that, even if there's so many attempts, I've gone to so many blogs and things, and you see all these attempts to try and explain how it's got to be the sun or this or that. And even if we could do that and say that the sun was strongly controlling it, there's something that's never addressed, which is why then are greenhouse gases not warming the planet? Which is an important sort of flip side to the question. It would be like if we put on a down coat and didn't get warm, that would be really weird, right? So you can't just say that it's the sun. Well, then if it's the sun, why isn't it greenhouse gases? Why is all this fundamental theory that makes a lot of sense and should be warming, why isn't that happening? And that's often ignored. And this is just one last line of evidence here. Sometimes people say it all hinges on climate models. We only know everything we know about climate has to do with these models that exist in computers somewhere, right? And models are very important. Models, but this is the only time I've ever showed you this whole talk, a model, climate model. Models are very important because we are doing an experiment without any replication on the planet. We can't tinker with the Earth and figure out how it's going to change. We're doing that, and we're going to have to wait and find out. Models are the only tool that allow us to try and figure this out. So these are like gigantic, basically sort of weather models in a way that are really run out long into the future. And when we run them with all of the factors, including greenhouse gases, the black is the observed, the orange and red is what the models produce. If we leave out anthropogenic factors and only include natural factors, we can kind of explain what's going on at the beginning of the century, but then the last 35 years, we just can't explain this at all. And so this is just another part of the evidence indicating that we really have no explanation for this other than greenhouse gases. And this, actually, I'm going to skip that and ask, where do we go from here? Right, so we've seen this. This is temperature rise. The small squiggle lines are monthly values. There's a lot of variation from month to month. And computer models are really important in figuring out where are we going to go. That's the only thing we can really do to try and make these projections that are necessary. And it all depends, obviously, on what we end up doing in terms of emitting greenhouse gases. So there's no one answer. So one potential avenue, and this is sort of a low end by the end of the century, this is out by 2100, a rise of maybe 2 degrees Celsius. And this is if we really limit greenhouse gases and basically don't double CO2. We kind of level off before doubling CO2. And this is if we sort of take a middle-of-the-road path, take a little bit longer to figure things out, how to get off of a fossil fuel-based economy. And then this is the scenario where we're very fossil fuel-based, very fossil fuel intensive. And so far, in terms of our emissions, we're tracking higher than this red scenario. We're putting out more carbon dioxide than these models had assumed. So we're getting up into really uncharted territory. And we've already increased about 1 degree Celsius in a century. It doesn't sound like all that much, right? Well, the ice ages were about, the difference between in the ice age and out of the ice age is about 5 degrees Celsius. Right? And the last ice age we came out over about 5,000 years. We increased 5 degrees. So it was about a degree per 1,000 years. And that was a dramatic shift. There's extinctions, there's migrations. This is a big deal, right? We just increased temperature 10 times faster, right, than the last ice age. And if we look at some impacts, which Nick is going to talk more about, as we start getting up into these higher and higher ranges, we start to have more uncertainty as we don't know what's going to happen up there. It's really hard to predict how ecosystems are going to respond. It's difficult enough to understand ecosystems. But as we get into this temperature range, which we might already be committed to, corals are very sensitive to temperature change. We may be getting into, no matter what, maybe getting into a world where coral reefs are bleached. As we get up into 2 to 3 degrees of warming, we have major impacts potentially in the rainforests. We have species that start to be committed to extinction. Coral reefs are probably extinct. Physiologically, they're not able to live in waters that warm. Oops. And then once we start getting up into this range, potentially, it's really hard to know what's going to happen. But all signs point to the fact that these are changes that most organisms are not capable of handling. So I want you guys to be thinking about this framework and thinking about how you critically engage issues and deal with complexity and don't shy away from complexity. Right? Embrace complexity and think about how does this new piece of information that you're looking at, how does this fit into the bigger picture? Right? And really start to try and think about the jigsaw puzzle model. Like this bit of information does not necessarily invalidate this other bit of information. You have to look at them both together, right? The whole thing is not going to collapse based on one thing that comes out. And so, ultimately, this is sort of coming down to a really big bet in terms of this grand experiment that we're doing about how the world will react to unprecedented greenhouse gas release, right? So those who are saying this is going to be fine and we shouldn't do anything about it are really making a big gamble, right? And what's at stake is a world that, the world that we evolved in, the world that civilization developed in. And I'm never a big fan of sort of the doomsday sayer aspect because we don't exactly know what's going to happen, but it's a huge gamble. It's a huge risk. And the probability that some really bad things could happen are no longer zero. Right? These uncertainties aren't very comforting. They're not a reason for inaction. Some of the uncertainties are on the other end of things, which we'd like to be very certain that a major change is not going to happen, right? Or that we're going to flip some switch and the whole Earth is going to respond differently. We don't know. We've never been into these places, right? So, we're making a big bet, and we're not really betting for us. We're betting for future generations. We're betting for all the species on the planet, And the thing is, though, with poker, you don't really know what the cards are, right? You have no idea. Maybe you can get at people's facial expressions or something. But we have a really good idea of what the cards are. We have a lot of information on this. People have been working very hard for a very long time on this, right? And they're not very good. So it's really important to put this in the bigger context of when do you have enough information to start acting, right? And when do you when are you able to take that capacity to really critically engage on topics so that you can take the time to make the right decisions, right? So I don't want you to just take this only within the realm of climate science. I want you to really try and apply some of this to all this information that you're getting from science and from other issues that are very complex and hard to deal with. And don't discount things that don't make sense to you. Right? Really try and dive into them, okay? And I just want to leave these for you guys. These are some really good resources online. This is a great site, Skeptical Science. They have an iPhone app with the 10 most used climate change arguments or skeptical arguments. It's a really great site. Lots of good information there. This is a little bit more hardcore science from top scientists. This is the Intergovernmental Panel on Climate Change. Very comprehensive synthesis of data. I would start here. If you have a question, if someone said, hey, it's global warming on Mars, it's got to be the sun, go here. But with that, thank you guys, and enjoy Albright.